So this is a integral that we can totally do in real life. It's the integral of sine of x. And if we go from here to here, we're looking at the area under the curve. So we have a positive area under the curve and a negative area under the curve. So that integral over here, this integral is 0. You can also do it with like actual math and doing cosines and evaluating it. But I mean, you just look at it, the area under the curve is clearly 0. However, in real life, there are only a small number of integrals we can actually solve by hand, and the rest we have to solve numerically. And so I wanted to do some problems where I'm going to solve like sine, which we know the answer, by hand, and then I'm going to do one that we can't do by hand, and that'll probably be in a separate video. But I'm going to just kind of show you how to do this, and then we're going to do it in Matlab. It's going to be amazing. Okay. So first of all, we're going to use a rectangle width of pi over 4. So I've put these little wonky-doos here so you can see where the pi over 4s are, just to kind of help you get a spot. So what we're going to do is we're going to draw in, and you kind of do this, I feel like, in calculus, but you do it to prove how you do things in real life. You don't prove it to show how you can't actually solve them in real life, and you have to do it numerically. Anyway, we're going to draw rectangles that intersect the curve on the left of the rectangle. So for example, let's see if I can kind of draw some of these little pink lines in. So like if I was kind of separating things like this, okay, so in this first section, this is actually a super tiny rectangle, right? Because it's just right there, because it's intersecting on the left. This intersection, or this rectangle here, will intersect on the left, so it'll intersect right there. This one will intersect here. This one will intersect here. And then here, this will be another 0 rectangle. So all these have a positive area. And then this one will go on the left here. And this will be a negative area. This one will be a negative area. And this one will be a negative area. Yay! Okay, so we have all these, areas, and we're going to add these rectangles to get an estimate for the sine. And again, I understand we know what the answer is. We're just doing this to practice so that we can get better at doing this bigger. And obviously, if you've taken calculus, then that's a giant D delta x. That's a giant delta x. And normally when we do calculus, we're doing the limit as delta x goes to 0. So clearly we're going to end up doing that eventually for Matlab, but that's how you actually have to do it, is you can't do this any other way except by estimation. Well, except for, I mean, even this is technically going to be an estimation, so I actually get a worse answer if I'm doing it computationally than if I just did it by hand. So, so this is what your picture is going to look like, and then in Matlab, what we're going to do is we are going to find the areas of each one of these, just kind of computationally. So essentially what it's going to look like is we're going to have a width, and I'm going to make it a variable just so that I have more flexibility later. Our x values are going to start at 0, they're going to skip by the width, and then they're going to go all the way to 2 pi, right? So 0 to 2 pi, skipping by pi over 4s. And then basically what we're going to do is we're going to calculate the area for each one of those rectangles, which is basically going to be the width times whatever sine is evaluated at the left-hand side. So basically, we'll just do it this way. So let's say we have some, it's going to be a for loop. We're going to go for our index going from 1 to, and actually we're not going to do all of these. We're going to have to do the length of x minus 1. I guess I could just be programming this, but I feel better writing this down to kind of get an idea. So basically, y'all understand, like, because this is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 points, but I only have 8 rectangles, so I can't go all the way to 9. I have to go to 8. So for I going from 1 to the length of x minus 1, the height of my rectangle is going to be the value of sine that is evaluated at the x in the ith position. So like x is going to look like 0, pi over 4, pi over 2, 3 pi over 4, pi, etc. And so what I'm going to do is I'm going to take the first one, so that'd be x at 1 is 0, take the sine of 0. Then I'm going to go x at 2, which would be pi over 4, and take sine of pi over 4. So it's a little weird because you have this nested function. I'm going to make it a little bit prettier. But the height is going to be the sine of x at the I location. Okay, and then we know what the area of a rectangle is, right? So this area or whatever of the rectangle is going to be its height times the width, which we have, and then basically we're going to update the total area. So we're just going to have a kind of like I guess I could just put this in here instead of discussing it. This area, so we could have like total area, and we always want to start it at 0 since we're going to be adding to it. Remember that 0 is like the neutral for addition. And then every time we want to go through this, we have the total area is going to be equal to the total area plus the new area. I think that should basically get it. So using that method, we should be able to estimate the integral of sine of x from 0 to 2 pi, of course, knowing that the answer should be 0. So let's see how this is going to work. I'm going to get myself a new script. New script, yay! I'm going to start, I'm just going to kind of separate these out. I'm just going to call this like part 1, problem 1, something 1. All right, I always start each script with CLC clear just because it clears out the command window, clears out the workspace, starting with a fresh, clean slate. So I'm just going to type out what I have here because we talked about it. And then total area 0. So for I. Now, technically in Matlab, it's better not to use I because technically I is the square root of -1. So I'm just going to change it to index. I will still work. It just means that I'm overwriting the built-in value of I, which just makes me feel guilty. For index going from 1 to length of x minus 1, I've got my height is equal to the sine of x at the index. And then this area is equal to the height times the width, which is, I guess, just w. And so the total area is equal to the total area plus this area. And the goal is that I should get 0. So I'm going to say this is lab 7. All right, so I'm going to go ahead and hit Control Enter to run this section. And it comes up with a super small number. Yay! So that's what I wanted. I was hoping we get something close to 0, which is kind of funny because you look at this and like, man, there's a giant like error right here. Like all this isn't getting included, and all this is getting included and shouldn't be, and all this isn't and should be, and is and shouldn't be. But it turns out that all of those things, they kind of counteract each other. We end up with actually a pretty nice little estimation. So this is basically the exact same thing, except now we're drawing on the rectangle intersects the curve on the right. So if I kind of throw these in here again, I'm intersecting on the right. So there's my rectangle intersecting on the right. Here's my rectangle intersecting on the right. On the right, this one's on the right. On the right, and this is a -1. On the right, this is a -1. This is a -1. And this is a -1. So it's actually the same code. And actually I can use the same, looks like basically the same thing. It's a little different, but it looks similar. In this case, the thing that I can do is just adjust my for loop. So before I was using the first 8 to get the heights. Now I'm going to use the second 8 to get the heights. So my index can just go from 2. My index can just go from 2 all the way to the length of x, because I actually want to go to the end of where x is, because I'm using the right-hand side to get the calculations. And again, as a reminder, I don't have to worry about the fact that this is negative, because the height will be negative. It'll make a negative area. But actually this one, once you've got the first one, drawing it on the right just takes a change in the, it just takes a change in that one line of code. So I'm going to do all this for the right of the circle. I'm just going to make this like a problem 2 or something like that. That's funny. Okay, and I just need to change this for loop. So for the index going from 2 to the length, I could also have just put an index plus 1 here, but I think this is a little bit more clear about what I'm doing. I'm going to go ahead and run with it. And look, yay, I get the basically 0 as well. So I'm feeling pretty good about this method, but of course, I always want to see if I can do slightly better. So I remember the first time that I took a class in this, this was like crazy because they made it sound like it was really, really, really hard. And it was a graduate level programming class in math. I was just like, what are y'all doing? And then like I got like more experienced and I learned stuff and I was like, oh, actually that wasn't that bad. Because they were like, compare the rectangle method with the trapezoidal method. I'm like, dude, you've got like a lot of big words in there. So anyways, all that to say that this is not supposed to be scary. It's supposed to be fun because we're estimating integrals. And when is estimating integrals not fun? Chirps and chirps. Okay, so basically what we're doing here is instead of drawing this rectangle here, where obviously you've got a lot of error going on right here, what we're going to do instead is we're going to draw a trapezoid because the idea is the trapezoid is going to fit the curve a lot better. So see, we're going to like connect, and then chirps, right? And then this one is going to connect, dupes. So now the error that we have is a lot smaller. It's just that little chunk instead of that monstrous chunk that the error used to be. So all of these little trapezoids are now going to get added together. Look how happy they are. This is going to take a while to draw. All right, and there was really no reason that I did those in multiple colors except that I thought it would make things look a little bit nicer. Okay, so again, we're doing the width is going to be... I'll just do width. The width on these is going to be pi over 4. So I'm going to rewrite the code out here just a little bit. But again, our x is going to go from 0. Come here, girl. Our x is going to go from 0, skipping by the width, all the way to 2 pi. So I guess you have to remember the equation of the area of a trapezoid, which hopefully you have. But if you have a trapezoid with 2 heights, it's like whatever your let me draw it. I guess I'll draw it the same way that we have it here. That's not really a good representation. So I have this trapezoid. If this is height 1 and this is height 2, then basically what you're going to do is you're going to average the heights. So this is height 1 plus height 2 over 2, and then multiply by the width. And that's really all there is to it, which makes sense, right? Because if you have a triangle, then it's just h1 is 0, so it's just h2 over 2 times the width. So yay, at least kind of looks like it might be right. So I'm going to do the left-hand height as height 1, and so that's going to go, oh, I got to put this in my for loop. Technically, this is Matlab. I don't think you have to use a for loop, but it's just a little bit easier to picture. So I'm still only have, where am I going with this? I still only have 8 rectangles, so my for loop can still only go 8. So I can't just ignore this, but basically what I'm going to have to do is I'm going to say, okay, so my first height is going to be sine of x at the left side value, and then my second height is going to be sine of x at the I plus 1 value. So basically whenever we get to 7, whenever I equals 7, this will be sine at position 7, and h2 will be sine at position 8. Or sorry, position 1, 2, 3, 4, 5, 6, 7. Hold on, I'm really bad at counting. 1, 2, 3, 4, 5, 6, 7, 8. That makes more sense. So the length of x is actually 9. There we go. See, this is hard. I mean, well, it's not hard. I shouldn't say that something is hard when I'm trying to like be like all experty about it. But anyway, so the length of x is actually 9. There's only 8 rectangles. So when this is 8, this is going to be the sine at the 8th position, which is going to be this position, and this is going to be the sine at the 9th position, which is right here. So we still get both sides of the rectangle by doing a little bit of a adjustment right here. But we do have to be careful because every time I do this, my first thing is to go, and guess what? Now we can go all the way over there, and I don't include that -1, but there's still only 8 rectangles. I keep calling them rectangles, shapes. You're not adding any rectangles or shapes. You're just changing the shapes themselves. But in any case, now the new area is going to be that h1. Come here, girl. h1 plus h2 over 2 times the width. And then we'll have to obviously add that to the pre-existing area, and then set a pre-existing area there. But this is, again, the whole goal is to see if we can make this to be 0. I'm going to write this one from scratch just because I'm probably going to forget what I'm doing. So I'm going to call this problem 3, and I'm going to start with the CLC clear. All right. Oops. All right. So what do I got? I got a width of pi over 4. I've got an x is going from 0 separated by width going to 2 pi. And I have to put in my total area. I can't spell. Total area is 0. All right, so for index, I'm going to call it index going from 1 to the length of x minus 1. h1 is going to be equal to the sine of x at index. h2 is going to be equal to, I can't spell, is going to be equal to the sine of x at index plus 1. So my new area is going to be h1 plus h2 divided by 2 times the width. So my total area is going to be my previous total area plus the new area. And then I end, and then I'm going to display my total area. And I should get, again, 0. Let's see if I get a better 0. Oh no, I broke something. What did I do? How did I break? How sad. Oh, I'm just dumb. I forgot. I got excited. Yay! I don't know if that's any better. What was the other ones? The other ones were like 10 to the negative 16 and 10 to the negative... this one isn't really noticeably any better, but, you know, it's just another way to do it. I feel better looking at the picture that it looks like there's less errors. I'm not relying on the fact that, well, eventually, you know, all the errors, you just kind of got to depend on them to cancel out. That freaks me out a little bit. But the nice thing about the sine function is because it's symmetric, it does make sense that our errors would kind of cancel out. And also because I'm taking symmetric shapes. If you look at all these shapes are all the same size.